So um, we've been doing what? We've been making a transition from vector quantities to scalar quantities to simplify our sort of life in research, life in science, right? Because dealing with vectors is less pleasant than dealing with scalar quantities, right? So that was the major, okay, yeah, the major sort of like a goal over the last 2, 3 classes, right? So what we've done, first, we replace the electric force, which is of course the vector quantity, and since it is a conservative force, we could introduce the gravitation, electrical potential energy, right? Electrical potential energy, which is a scalar quantity, and both of these things, force and the potential energy, they both describe interaction, right? So that was our first step, and then in the previous recitation class, and some of you will do it today, right, in your recitation class, which will be in the afternoon, right? So we introduce the electric, instead of electric force, or instead of electric field, we introduce the uh, electric potential. Electric potential. So, and both of these quantities again describe exactly the same thing. If you have some electrically charged object, electrically charged system, of course, that system creates an electrical aura. Up to this point, we describe that aura using the electric field, right? But now, again, since it's a vector quantity, now we introduced the electric potential, which again describes exactly the same electrical aura created by a charged system. So again, this and that describes the same thing. So if they describe the same thing, of course, there must be some relationship, right, between these two quantities. There must be. And the main goal of today's class is to establish these bridges. So we need to find out how can we move to, for example, electric potential from the electric field, or how can we move from the electric field to the electric potential, right? Uh, why do we need these bridges to go back and forth between the electric field and the electric potential? I can give you some simple example. Let's say you work with in your research with some electrical system, and it can be complicated. And let's say you need to know the electric field. And of course, if you try to integrate electric field to find the net electric field at some point, it can be ridiculously complicated, right? So what can be done instead of trying to get electric field directly? You can make a transition to the electric potential, scalar quantity. Integration will be easier. Find the electric potential, and then only move back to find the electric field. Okay, it's kind of longer sort of trip, but easier. And quite often it's done in research, right? So that's why we need to be quite comfortable moving back and forth between these two quantities, right? Okay, so but we will start finding this relationship maybe like in 5-10 minutes. First, let's practice a little bit, practice working with the electric potential, right? And also, since we introduced new quantity electric potential, what about units, SI units? And yes, we need a special, not need, we introduced the special SI unit because electric potential is used by tons of people. Technicians, engineers, right, experimentalists, right? Electric potential is almost everywhere. So it makes sense to simplify their life. And instead of pronouncing every time, so 5 joules per coulomb, 7 joules per coulomb, it can be annoying, right? So it makes sense to introduce the special unit, volts, 5, 7 volts, right, and so on. It's much more convenient, right? Okay, so units is there. So now, what we didn't practice in our recitation class about the electric potential is principle of superposition. And now, working with principle of superposition, it's a piece of cake. Let's imagine this situation that we have 3 charges, 3-point charges, Q1, Q2, and Q3, right? You see them. And let's say we want to find the net electric potential, for example, at this point P, at this point P. So what can be done? So first we need to find contribution to the net electric potential from this charge Q1, and we know how to do it. We derived that formula again in the previous recitation class. Some of you will do it today. So the formula is kq divided by r, where r is the distance from the charge to the point in question. So that will be contribution to the net electric potential from the first charge Q1. It's just a number. Let's say it will be 5. Then do the same with the second charge. Of course, that contribution will be negative because this charge is a negative charge. So the electric potential around this charge will be negative everywhere. And of course, 0 at infinity. So that will be contribution to the net potential from the second charge. It may be, let's say, minus 3 volts. And then the same, exactly the same story with the last charge, Q3. Again, you just need to find the distance to the point in question from the charge, calculate this construction kq over r, add 3 numbers, and that's it. What not to like, right? There will be, in your homework, there will be similar problem. You will have like 3 charges positioned somehow, I don't know, maybe at the corners of a rectangle or triangle. So geometry will be given. Basically, you will have to find some distances, right, and calculate these contributions, right, and add several numbers, right. So it will be in your homework. So you see how much easier when we applied principle of superposition with the electric field. You remember how much we struggled. It was, I think, in the second recitation class, right, with those vectors. And and now it's so simple. That's the goal of moving from the electric field, from the vector quantities to scalar quantities. Right. Okay, so now the question for you. On the exams, I like giving questions like this. So what do we have here? 2-point charges. Basically, it's a dipole. Plus Q, minus Q, right? Then there is a midpoint, right? So this distance and these distances are the same, right? And so, of course, around these 2 charges creates the net electric field and the net electric potential. So exactly the same aura can be described either using electric field or electric potential. So the question is about this midpoint. Which statement is correct about the electric field and the electric potential? Electric field 0, potential 0. Electric field 0, potential positive, then 0, negative. Then E points to the right, electric potential 0, or E points to the left, potential 0. Okay, so I created 3 poles, right? So scroll up, right, to concept test 1, right? You see that it's a concept test 1, then 2, and then 3, right? And give it a try, all right, and then I will discuss. Right? So which statement is correct in this case? And I'll get some water. Let me see your answers. Okay. Okay, I like the distribution of your answers. Okay, looks encouraging. Yeah, about the exam review session, I tried to record everything, right? An exam review session I started recording several years ago, and every time, if everything works fine, all right, of course it will be recorded and posted as usual. Okay, I guess I can discuss because we need to move. Um, so let's start with, for example, electric field first. Okay, we know how we can find the electric field. Let's start with the positive charge, right? You can think about, you can imagine positioning a probe charge, small positive probe charge over here, or just recall electric field lines. Both ways work. So positive charge, point charge, of course, is going to create electric field pointing to the right that way, right? So that will be E. Oh, let me press on slides. Okay, right. So that will be a contribution to the net electric field from the positive charge. Then negative charge, you remember electric field lines, they end on the negative charge. They go towards the negative charge. So as a result, electric field at this point will be towards the negative charge, right? So we have two contributions. They are in the same direction. Of course, they add each other up to stronger net field pointing to the right. Right. So immediately it gives the answer, right? So even just analyzing electric field, you can see that the right option is option D, right? So now let's just confirm that the net electric potential is 0 as well. So principle of superposition. So what I've been doing, right? I just applied principle of superposition, and now principle of superposition for the electric potential. Let's just add two numbers, because electric potential is a scalar quantity. So V at the point equals V1 plus V2. Actually, I should have used probably V plus and V minus, but it's not a big deal. So contribution from the positive charge will be K Q over R. And from the negative, minus KQ over R. R's are the same because this is the midpoint between the charges. And these charges are the same, but of course this is positive and these are negative, the same in absolute value. So positive gives us positive contribution, negative charge is going to give us negative, the same but negative contribution at the midpoint. So let's say plus 5 volts and minus 5 volts. Of course, you will end up with 0, right? So of course, the correct answer is a D. And so I found this plot somewhere, I don't remember, maybe in the book, right? So three-dimensional plot, how electric potential changes with point in space, right? So near the positive charge, we have a spike, positive spike, right? And then the potential goes to 0. But around negative charge, we have a negative spike, and then electric potential goes to 0. But our point is here, midpoint. So both contributions just cancel each other out, giving us the 0 net electric potential. Okay, so based on your answers, you got it. This you shouldn't have significant troubles. Now I think it's time for me to write something. Yeah. So you remember that example, which we already practiced, right? So you remember a charged ring, and at some point, I don't know, a couple of weeks ago, I found the electric field at the distance z from the center of the ring. At that time we found the electric field, and now we introduce the electric potential instead of electric field. Let's see how much easier integration is going to be this time in order to find the electric potential instead of electric field. Okay, so let me switch to the whiteboard quickly. And okay, so this example, that will be the second later on. So we have a charged ring, radius is given, and the total charge Q is uniformly distributed over the whole ring. And we need to find potential at that point, which is the distance z from the center of the ring. right? Okay, so again, the beginning is exactly the same like with the beginning when we try to find the electric field. So you take, maybe I should use this. You take infinitesimally small section of this ring with length dl. And of course, there will be some small amount of charge dq on this section dl. It's infinitesimally small. It means that it's smaller than anything you can think of. It means that we can treat it as the point charge. You remember these words at the beginning of that example a couple of weeks ago, right? So it means that I can treat it as the point charge, and we know the expression for created by a point charge. You remember V equals K U over R, right? So that's we derived the formula which we derived, which describes the electric potential created by a point charge Q at a distance R. But now our point charge is dq, so we can use it. But now, of course, I'll have to write dv equals K dq over R, right? And what is R? R, of course, it's a distance from our point charge to the point in question. So this is R. So now what's next? Before we can start integrating, we need to write all these quantities in terms of what is given and in terms of variable of integration. Given, we see what is given, ZRQ. Variable of integration, it's more complicated to see from the very beginning what will be the best variable of integration, right? But as you start moving, sooner or later, you will realize which variable is the best. So R can be easily written in terms of what is given. All right, so it will be what? This is the right triangle, right? So it will be R capital squared plus Z squared and square root out of that. So it will be R squared plus Z squared. And you know what? Let's start integrating immediately. So I will write, so V equals integral over the whole ring of dv, right? And let me rewrite with that new R. So it will be integral of K dq over square root of R squared plus Z squared. And at this point, I should probably ask, what? So is it a complicated integral? Let's analyze. K is the constant, can be taken outside. This denominator, R is constant, it's a given. Z, it's also given, it's some number, right? It's a given number, a certain distance at which you want to find the net electric potential. So all this construction is constant, and it can be taken outside of the sign of integration. And as a result, okay, let me write over here, V equals, so that constant can be taken outside. And integral out of dq over the total ring. So in this case, look, so what is this? It just means take dq plus another dq, small charge, plus another plus, and you keep adding those small charges, moving around the ring. Of course, when you complete the motion and come back to the beginning, of course, you will end up with the total charge of the ring, total charge of the ring, right? So this is equal to Q capital. So in this case, even dq, so we use q as the variable of integration, right? In that example, we use L, right? Element of this ring, but now even dq is enough. So as a result, we're getting the answer. So it's a K, Q capital, divided by square root of R squared plus Z squared. You see how much simpler this is. And I want to emphasize on one thing also. Look, before, you remember when we wrote dE in that example 2 weeks ago, we had a vector over here, but now I did not draw anything because it's a scalar function, electric potential. It doesn't have any direction. It's just a number, right? So that's why there are no any vectors. We didn't have to decompose x, define the x direction, y component, x component, right? So piece of cake. Now it's so much easier. And again, that was the goal of making a transition from vector quantities to scalar quantities. So you can, in terms of troubles, you can go to scalar quantities, play with your system, and then once you found the result, you can go back to the electric field and find the electric field. Right. So it's much easier. Okay, and now at this point, we will go back to slides and we'll start building those bridges between the electric field and the electric potential. Yeah, building bridges, not walls. All right. So that is the example which I just discussed, right? And now, as I said, let's move further. So now let's find the connections or establish a relationship between the electric field and the electric potential. And first, let's build a bridge which will allow us to go from the electric field, E, vector quantity, to a scalar quantity, the electric potential. So from E to R. Right? And then, of course, maybe in 10-15 minutes, we will move in the opposite direction. I will go through some simple derivation, right? And I will, since it's not that complicated, I'm going to use slides. I don't want to go to the whiteboard. So let's assume that we have some point charge over here somewhere, right? Point charge Q. And let's assume that this point charge is moved, or it moves from some initial point there, initial point, to the final point. Completely arbitrary path. I emphasize on this, completely arbitrary. And okay, of course, let's assume that it's exposed to some electric field, because you remember what we want to get? We want to move from the electric field to the electric potential. So we assume that the electric field is given. And now we need to somehow connect it to the electric potential. And now for fun, just let's calculate work done by the electric force. So we have the charge, of course it is going to interact with the electric field. Of course we can introduce the electric force, and let's calculate the work. Since there is a force, there is a displacement, so let's calculate work done by the electric force. So let's start recalling physics 1. We already used this expression a couple of times in this semester. Work done by the electric force as this charge moves from the initial to the final point. It's a F dot ds. So now our goal is somehow to bring into this formula, in this side, electric field, and on this side, the electric potential. Because yeah, that's what we wanted to get. And first of all, what is ds? Ds, that's this infinitesimally small displacement, ds, right? And so now again, recall from physics 1. Since work is a conservative force, right? So we can introduce potential energy, and as a result, we can connect work by this conservative force with the change in the potential energy. Again, in physics 1, work equals to the negative change in the potential energy. Again, we used it already once in this semester, right? So that's what we're going to write instead of this W, minus delta U. But of course, I will move minus to the side of the integral. So it will be equal to delta U equals minus integral of F dot ds. So now probably you see immediately, right? So instead of force, we can easily introduce the electric field because we know the relationship F equals QE. And we also remember from the previous recitation class that potential energy and the electric potential are easily connected. So from here, we can easily introduce the electric potential, and from there, we should be able to introduce easily the electric field. right? So first, electric field. Of course, F equals QE. So Q I can take outside. We'll get minus Q integral of E dot ds. And now, since the electric potential was introduced as potential energy divided by the charge, so if I take this charge, Q, move it to this side, in the denominator under delta U, so delta U over Q will be my delta V, and that's the derivation. So as a result, yeah, as I said, delta U over Q, it's a delta V change in the electric potential, and what's left on the right-hand side is just this minus and that integral only. As a result, we're getting the bridge which we needed. Delta V, which is what? It's a change in the electric potential. Delta V, it's a value of the electric potential at the final point minus value of the electric potential at the initial point. So you see, we're not connecting directly electric field at a certain point with the electric potential. No, we're connecting the electric field with the change in the electric potential between two arbitrary points, final and initial. So we're going to use this formula from time to time, I would say often. All right. So again, that is the bridge which allows us to move from the electric field to the electric potential. And again, it connects field with the change in the electric potential. So now, of course, strictly speaking, this integration is far from being trivial, right? Every time in this course, we end up with some integration over a line or integration over a surface, and those integrals are not trivial. It's a calculus 3, and most of you are not familiar with that, but you saw how we treated the integrals in Gauss's law. Exactly the same we're going to do here. We're going to avoid integrations, but still we're going to evaluate those integrals. Crafty, sneaky, right? Okay, so what we're going to do with this integral. Okay, let me move to the next slide. All right, here. So this is the formula which we just derived, right? Let's write explicitly this integrand E dot ds. Of course, it will be what? E ds times cosine of angle between them. Right? Okay, let me restore the picture from the previous slide. Right. So this is the picture from the previous slide. I just copied and paste. And look, what is E times cosine of angle? The angle is this, right? Angle between this electric field and ds. So if you take a E and multiply by the cosine of that angle, what are you going to get? You're going to get component of the electric field along the direction of motion, along S, E cosine theta, you see? We're just finding component of this electric field along the direction of motion. So I can rewrite this integral as negative integral of E sub S, it's a component of the electric field, times ds. And now recall graphical interpretation of any integral. It's an area under a curve if you plot integrand versus variable of integration, and area under the curve, that's the value of the integral. So in this case, if I plot E sub S, this E sub S versus S, this, you see? If I plot E sub S versus S, then, and of course, this is some initial point that's you see in the integral, lower limit and upper limit, right? So it's a beginning and the end. So area under this curve, it's the value of the integral. But of course, don't forget about this minus in front. So so instead of calculating integral, we're going to calculate area. Most of the time, this plot is going to be a straight line, right? Either horizontal or going up or going down, right? But every time it will be a straight line. As a result, finding area is trivial. But don't forget about the minus. Find the area and add the minus in front in order to find the potential difference. It's a common mistake, silly mistake, right? Students tend to forget about minus. Once I remember even I forgot to, at some problem I remember I made that mistake, right? So don't forget about the minus. So that's what we're going to do. We're going to use this trick. Instead of taking integrals, we're going to calculate area. But if you're comfortable with taking integrals, go ahead and use that and integrate. Not a big deal. Right? We as instructors should be able to understand what you do. If what you do is correct. Okay, so that's what we're going to do. Just calculate area. Right? And now let's start looking at examples. And I think now it's time for me to go back to the whiteboard and look at the second example which I prepared. And then there will be another clicker question. Right. Okay, probably I'll start switching. Let me check if I'm correct. Yeah. So now the example. Okay, I think should be enough time. All right, so let me switch. We have here markers. We have some information about the electric field given in the form of this graph. So you see graph, x component of the electric field, units of volt divided by meters. So up to this point, every time units of the electric field, we use newtons divided by coulombs. But it can be easily shown that newtons per coulomb equals to volts per meters. Maybe in the recitation class we will go through that, but even by yourself you can easily convince yourself in that, right? Volts divided by meters, units. And then versus x is in meters. And you see the plot, straight line, this red line. So when x equals 1 meters, the value of the electric field is 1000. And again, what does it mean electric field positive? You see positive electric field. It means that it points in the positive x direction. Electric field is the vector, right? If we had some values of the electric field negative, it means just it points in the negative x direction. That's the meaning, right? Okay, so what we need to find? We need to find how electric potential changes with x. So we need to find function. You know what I probably should emphasize? It's a function, right? So we need to find function, how v changes with x. And some additional piece of information is given. Problem says, assume that the electric potential at the origin is 0. So we have plenty of information about the electric field and a small piece of information about the electric potential. So at this point, V equals to 0. Basically, the problem gave us a reference point for the electric potential, right? Okay, so we need to find this function. And so we need to use the bridge which we just derived. So we need to move from the electric field to the potential, right? And the bridge is, okay, let me rewrite it. So it's a delta V, which is V final minus V initial equals to minus integral from initial to the final point of ES ds. Okay, so that's in general. You can apply this formula for any initial point, for any graph, and so on. So no restrictions for this formula. So now we just need to apply this formula for our particular case. So first of all, direction of S, it's a x, because we have x component of the electric field and we see how it changes with x. So instead of S, right, we're going to have x. So instead of Es ds, we're going to have ex dx. Then we need to make a decision which point we're going to treat as the initial point and which point is going to be our final point. Okay, so let So which point, again, it's up to you. You can use any point you want. But since we have some information about the electric potential at the origin, it makes sense to take this point, x equals 0, as our initial point, right? As our initial point. So let x equals 0 be our initial point. Now, what about the final point? And usually at this point, I bug students, right, in the lecture, right, when we are at school, right, normal semesters. And so far, okay, I ask, so which point should we take as the final point? And so far, all the time, students give me something like this. Let's take, for example, they said point 2 as our final point, or point 1 as our final point. But look, what are you going to get if we take, for example, point 2 as our final point? So this will be v at point 2. This will be v at point 0, right? V at point 0 is 0. And when we calculate this integral, we will get the value of the potential at point 2 only at that particular point. But what do we want to find? We want to find the function. So we don't want to find the value of the potential at a particular point. So taking a particular point, in this case, it's not wrong, it's not good. So what do we have to take? Some arbitrary point x in order to find the function. Again, if the question was about finding potential at a particular point, yeah, that we would take that point as our final point. But now, since we want to find the function, okay, a function, we need to take an arbitrary point x somewhere on the x curve, right? So let me write it. Let an arbitrary x be our final point, and emphasize arbitrary. Otherwise, we wouldn't be able to get the function at the end. Okay, so now after this 3 small steps, now we can rewrite our formula. So now we are ready to calculate, right? So now we can apply it. So delta V, of course, it will be V at x, so it's our final point. So now I wrote V at x. Probably I should show that this is our x arbitrary. For example, this is our x arbitrary point x, right? So this. Of course, you can put it here or there, it doesn't matter, just completely arbitrary x. Right, so this is v of x, and this is initial point is 0, so it's a minus v at 0, right? X equals 0. And that integral minus integral from 0 to x of ex dx. If you're familiar with integration, you can easily integrate it, but let's use the trick which we just discussed. Let's calculate area, because this curve, I mean this integral is just the area of a triangle. Let me label it, this triangle, like this. Point O, point A, and point B. It's the area of this triangle, right? Area under the curve, area of that triangle. So area of a triangle OAB, right? So finding area of a triangle, yeah, 1 over 2 times height times the base, right? And also V at 0, it's 0. It's given. It was given in the problem. So this we can dump. Okay, so now we can write, so it will be minus 1 over 2 area of a triangle. Then base is x, you see, x. And then height. In order to find height, we need to know this distance, right? In order to write that down, we need to know the function of e versus x. So how can we write the equation of this line? All right, so e equals, so we need to, since it goes through the origin, So it's just the slope times x. How can we find slope? We know the value of e at 0.1. So the slope will be 1000. You remember slope, it's just a tangent of this angle. Tangent of this angle, it will be 1000 versus 1. So the slope is 1000. So equation of this line, it will be 1000 times x. All right? It's just a high school stuff. How to write equation of a straight line. So as a result, this height, since it's x, so this will be, height will be 1000 times x. So that's the height. So base is x, and this height is 1000 times x. So now I can write it here. 1000 times x. All right, so it's a base and height. Okay, so thousands divided by 2, it will be 500, so we'll get minus 500, and we have x and x squared. So eventually, so here we have v, here's our result, so as a result we can write v of x equals minus 500 times x to the power of 2. So that's the function which we wanted to find. We can actually plot it probably, right? So if you plot v versus x, it's a parabola, right? It's a parabola with the branches down because of minus. Since we know we have information on the x, positive x side, so let me draw this parabola like this. And if this is 1, then this should be minus 500, right? If x equals 1, the value of v will be minus 500. So that's the plot. So this is the function and plot how the electric potential changes with x. So that's how electric field changes with x, and that's how electric potential changes with x. Right. But again, I emphasize, so if the question was about finding the electric potential at point 1, we would take that point 1 as our final point. But since in this question, in this problem, the question was about function, yeah, we had to take an arbitrary x. Okay, so that's the example. And after this, we can go back and I will ask you a clicker question, another one. Okay, and the question, okay, I need to press on slides. Good. So this is the example which I just discussed, right? And the question for you, very similar. You see what is given? Information about the electric field. And again, you see x component of the electric field. So in this course, all the time, we're going to have only only one-dimensional situation. How x component of the electric field changes with x. No two-dimensional or three-dimensional cases, right? So you see the plot, how electric field changes with x. And additional piece of information again is given, right? So it says, assume that the electric potential at the origin is 0. Basically, again, they give us a reference point, right? Without that pieces of information, we wouldn't be able to find the value of the potential. We would be able only to find delta V, right? Change delta V, you see, right? Okay, so what's the value of the potential at this point, x equals 1? Okay, give it a try. And of course, I open up the formula, right, which we need for to analyze problems like this. Right. Okay, let me look at your answers. Now it's a question 2. Right. Okay, I see. Changes. Okay, we need to get information about the electric potential. I see that the leader is 0 volts. 0 is the electric field at that point. Why would we get 0 potential? Again, you just need to calculate area, you remember? And again, usually, at least on one of the exams, I give a question like this, right? Maybe second or first midterm, or maybe final. Okay, so now we have a different leader um, among answers. And so it means that you're forgetting about another thing, very important. You see what is in front of this integral? It's a typical place for mistakes. Don't forget about minus. Lots of students, especially at the very beginning, they made that mistake, right? Okay, so now after my corrections, I see that the correct leader is in front of all these options. Okay, so yeah, basically I answered, right? So now I see that plenty of you changed your mind, right? Okay, good. So it means that you understand what I'm talking about. Okay, great. So let me discuss it. But actually, I already told everything. So again, we need to make a decision which point is initial, which point is final. Since information about the electric potential at the origin is given, so that will be our initial point, x equals 0. And now, of course, the final point will be point 1 because we want to find the electric potential at the particular point 1. In the previous example, we wanted to find the function, okay, the function, right? So we put an arbitrary, we choose an arbitrary x, but now it's 1, right? And so now we just need to calculate area between, area under this curve, basically area of this triangle. It's 1 over 2 times base, which is 1 meter, right? And times the height, which is 2000. And of course, don't forget about minus, right? So let me finish discussing this. All right, so V initial is 0 because that's our piece of information which is given, right? And then area under the curve, negative 1 over 2, 1 times 2000, so it will be negative 1000 volts, right? Okay, so again, don't forget about minus. Okay, so what I've missed, right? So we haven't built the bridge in the opposite direction, how to get the electric field out of the electric potential, but it's very simple. We will do it in our recitation classes on Monday and Tuesday, right? I will tell recitation instructors to cover this. It's basically we'll have to use exactly the same formula, right? This, not basically this which is shown here, but we just needed to turn it inside out because all the needed quantities are here. We have the electric potential, we have the electric field. We just need to invert it, write it in a differential form, and that will give us a bridge how to move from the electric potential to the electric field.